Good day to all. This video will be on our machine learning project. We are Group 25 and our members consist of Yurong, Kahui, Rachel, Arvind, and Yumin. These are the points we are going through. This table shows the roles and contribution of the members for this project. The Kaggle project we chose was Women in Big Data South Africa, specifically the increase in female-headed households at risk of poverty. It is important to obtain accurate estimates of statistics in order to bring about an effective solution. However, current data collection methods has proved intensive and time-consuming. This project therefore serves to build a predictive model to accurately estimate the percentage of female-headed households in each ward living below a particular income threshold. The methods used are as follows. First, we analyzed the data set for pre-processing. Then we extracted features relevant to the project from various data sets and combined them with the training data set. This new data set is split into two subgroups for cross-validation. X contains features while Y contains the churn result of each user. The two subgroups, X1Y1 and X2Y2, will be used as the training set and test set respectively. We fit a classifier model on the training data set and evaluate prediction on the test data set. This is repeated with other classifier models using different parameters to observe any improvements. Prediction on the official test data set will be done on the best model with fine-tuned parameters. Methods such as random forest, cat boost, XG boost, and light GBM were used. Data pre-processing is an important step in machine learning as the quality of data and the useful information that can be derived from it directly affects the ability of our model to learn. Hence, it is extremely important that we pre-process our data before feeding it into our model. Firstly, we removed all NaN values in the dataset and replaced them with the integer 0. The dataset is also min-max normalized into a range between 0 and 1 to reduce the range of the dataset to have smaller standard deviations, which can suppress the effect of outliers. Next, we applied k-means clustering of longitude and latitude for geolocation clustering, which could be a factor for income level around the wards. We determined the optimal number of clusters by plotting an elbow curve and identified the point where its reduction in inertia is almost a constant. In our graph, we used 5 as the optimal number. This is because the greater the number of clusters, the more computational power is required for both data pre-processing and model training. The cluster labels visualized shows that majority of data are tightly clustered, which might indicate more female heads of family within the area. However, this conclusion might not be true as the data are collected with specific demographics in mind. We realized that some data are unbalanced and heavily skewed, which might potentially affect the results. Hence, we applied the synthetic minority oversampling technique to improve the model training. SMOTE uses the KNN technique to normalize the dataset, preventing oversampling of minority classes with imbalanced data. Feature engineering is the process of using domain knowledge to extract features from raw data. These features can be used to improve the performance of machine learning algorithms to save time and computing resources. An example of feature engineering would be using our knowledge and understanding to categorize the dwelling type. This is an attempt for training model to draw correlation and causation to the data set. We created some features based on our research into metrics of poverty. Some examples are listed in this table. For example, nearby pipe water access, which would indicate access to basic services such as clean water. Another example would be Manhattan distance between wards, which indicate size and accessibility of ward, and could impact poverty as rural areas tend to be further apart compared to urban areas. Feature extraction involves reducing the number of resources required to describe a large set of data. When performing analysis of complex data, one of the major problems stems from the large number of variables involved, which generally requires a large amount of memory and computation power. Also, it may cause a classification algorithm to overfeed to training samples and generalize poorly to new samples. Feature extraction constructs combinations of variables to get around these problems while still describing the data with sufficient accuracy. Optimized feature extraction is the key to effective model construction. Here for feature extraction, we used a form of principal component analysis to reduce the dimensionality of our dwelling features. Dimensionality reduction here refers to techniques for reducing the number of input variables in training data. Fewer input dimensions often implies correspondingly fewer parameters or a simpler structure in the machine learning model, being referred to as degrees of freedom. A model with too many degrees of freedom is likely to overfeed the training data set and therefore may not perform well on new data. It is desirable to have simple models that generalize well, and in turn, input data with few input variables. This results in the data set being more compact and easily interpreted, allowing us to identify the relevant important variable which affect the target variable the most. This is the sample code that shows the dimensionality reduction for the dwelling features and the language features. Feature importance refers to techniques that assign a score to input features based on how useful they are at predicting a target variable. Feature importance scores play an important role in a predictive modeling project, including providing insight into the data, insight into the model, and the basis for dimensionality reduction and feature selection that can improve the efficiency and effectiveness of a predictive model on the problem. These are some of the techniques we used to extract the important features: Pearson's correlation, lasso CV, XGB regressor, random forest regressor, LGBM regressor, and last but not least, cat boost. Pearson's correlation is a useful way of measuring the linear correlation between two sets of data, X variable and the target Y variable. The formula shown here is used to find the correlation coefficient of the two sets of data. Using the formula, we derive that PSA_00 is the variable that has the highest Pearson's correlation as compared to the other variables. The target is directly correlated as it represents mapped against itself. This is the lasso CV regressor feature importance model. Here we are able to observe the following features: PSA_00, lin_00, and PG_03 are strongly correlated with the target variable. Lasso regression is a popular type of regularized linear regression that includes an L1 penalty. The L1 penalty is a popular penalty used to penalize a model based on the sum of the absolute coefficient values. An L1 penalty minimizes the size of all coefficients and allows any coefficient to go to the value of 0, effectively removing input features from the model. This has the effect of shrinking the coefficients for those input variables that do not contribute much to the prediction task. This penalty allows some coefficient values to go to the value of 0, allowing input variables to be effectively removed from the model, providing a type of automatic feature selection. XGBoost stands for Extreme Gradient Boosting and an implementation of gradient boosting machines created by the renowned developer Mr. Tiankai Chen. The XGBoost library implements the gradient boosting decision tree algorithm. Gradient boosting is an approach where new models are created that predict the residuals or errors of prior models and then added together to make the final prediction. It is called gradient boosting because it uses a gradient descent algorithm to minimize the loss when adding new models. XGBoost makes use of different system optimizations such as parallelization, tree pruning, and hardware optimization to improve upon its own results. It also has the following algorithmic enhancements: regularization, sparsity awareness, and finally cross-validation, in which the algorithm comes with built-in cross-validation method at each iteration, taking away the need to explicitly program this search and to specify the exact number of boosting iterations required in a single run. Here, PSA_00, PW_03 and PG_00 are the variables which mostly correlates with the target variables using XGBoost regressor. Random forest is a supervised learning algorithm which uses ensemble learning method for classification and regression. Random forest is a bagging technique and not a boosting technique. The trees in random forests are run in parallel. There is no interaction between these trees while building the trees. It operates by constructing a multitude of decision trees at training time and outputting the class that is the mode of the classes, classification, or mean prediction, regression, of the individual trees. A random forest is a meta-estimator, i.e. it combines the result of multiple predictions, which aggregates many decision trees. For random forest, LAN_06, LAN_02, PSA_03 are the variables which mostly correlates with the target variables using random forest regressor. Light GBM, short for Light Gradient Boosted Machine, is a library developed at Microsoft that provides an efficient implementation of the gradient boosting algorithm. Therefore, it is a framework based on decision tree algorithm, used for regression, classification, and many other machine learning tasks. Since it is based on decision tree algorithms, it splits the tree leaf-wise with the best fit, whereas other boosting algorithms split the tree depth-wise or level-wise rather than leaf-wise. The primary benefit of the LightGBM is the changes to the training algorithm that make the process dramatically faster, and in many cases, result in a more effective model. Advantages of LightGBM are not including faster training speed and higher efficiency, lower memory usage, better accuracy than any other boosting algorithm, compatibility with large datasets, and it supports parallel learning. Here the results show that LGBM regressor shows that car_00, family and PSA_00 are the variables which mostly correlates with the target variables using LGBM regressor. CatBoost is a recently open-sourced machine learning algorithm from Yandex. CatBoost is able to work with diverse data types to help solve a wide range of problems that businesses face today, and it provides best-in-class accuracy for many problems. CatBoost is a gradient boosting machine learning algorithm, as this library is based on the gradient boosting library. However, CatBoost introduces two critical algorithmic advances: the implementation of ordered boosting, a permutation-driven alternative to the classic algorithm, and an innovative algorithm for processing categorical features. Both techniques are using random permutations of the training examples to fight the prediction shift caused by a special kind of target leakage present in all existing implementations of gradient boosting algorithms. Here CatBoost predicts that PSA_00, car_01, and car_00 variables are mostly correlated with the target variable. These are the results against the Kaggle competition, our challenges and conclusion. This slide showed the result in our leaderboard. We made multiple submissions over the span of the project duration, and we did multiple testing. At first, our score was not satisfactory, ranging from 4.3 to 4.8 when the top scorers are getting around 3.5. However, after multiple trial and errors and trying smote, we managed to get a decent score of 3.6964. Comparing this score against the leaderboard, we are approximately 78th place, which made us to top 40% of the leaderboard, or 39.8%, to be exact. Figuring out what features are important. The main problem that we face while doing the project is that we do not know what features are important, so there was a lot of trial and errors involved. At first, we thought through data cleaning and plotting, we can find out those features, but that was not the case. Next, we tried applying multiple algorithms on the dataset and see each algorithm result. How we managed to solve this problem is through applying different algorithms and see their result. We can determine those features that are important. Time management. Our next problem is more external, which is time management. Despite having a reasonable time to finish this project, this is still an issue because of our other modules. Some of us was taking multidisciplinary project and advanced software engineering, which is also a huge time sink. Additionally, due to our lack of knowledge about data science in general, we also need to do our own research and studies to complete this project. How we solved this problem is by using a divide and conquer approach. We break down this whole project into manageable parts and assign each members to do and give each task a certain deadline. This way, we can prioritize what is important among our other modules as well and do certain tasks accordingly. Over the duration of this project, we realized that feature importance and engineering is a very important aspect. Using the correct variable is directly affect how good the end result is. Hence we have found out that the top 3 variables are attend school, PSA_00, owning a car_00, and access to tap water, PW_00. Even though feature importance is an important part of the project, it is not where we spent the most time with. It is actually the initial stage of cleaning and organizing of data. Though it may be a very tedious stage, it is also equally important, as ensuring the data is properly organized and cleaned can make the later stages easier. Lastly, this project has taught us to think outside the box. There are many times where we are constrained by our lack of knowledge and fixated on doing it a certain way, and this has led us to think outside the box. Be it to do more additional learning online or think of other ways to solve certain problems. With that, we come the end of our presentation. Thank you for watching.